Hi, everyone. Welcome to the first Local Talk session. We're so excited that you're here physically and virtually through Zoom and Facebook. My name is Sarah Kokirizandagire, and I am a graduate architect. And today I'll also be your moderator. So before introducing our speakers, I'd like to thank the Friends of Mustardseed for giving us the opportunity to realize this project. Would also like to thank the Uganda Society of Architects for supporting this event. And I'd also like to note that for the people watching the webinar, it is being recorded as we speak. So in case you encounter any connection issues, we'll send you an email with a replay link. Now, I'm going to briefly dive into some background information, the what, where, and why, as well as a brief version of the agenda today. So Localtalks is a new series of quarterly events, and by that I mean the sessions will be held every third day of every third week of every third month of the year. So save those dates. This session that we're having right now is actually supposed to be in March, but due to the pandemic, we had to postpone it. But here we are. So do save the dates in March, June, September, and December. Now, these sessions are meant to bring together people who are interested in and passionate about green design, architecture, and construction in East Africa and the world over. It is curated by Localworks, which is a multidisciplinary build and collaborative. It comprises of architecture, landscape design, civil and structural engineering, mechanical and electrical engineering, quantity surveying, and project management. And it specializes in the realization of ecological architecture. Localtalks essentially fulfills the share aspect of the 4 building blocks of Localworks. So the 4 building blocks are research, design, build, and share. And the aim of these talks is to create an open forum for exchange of ideas, honest debate, and knowledge sharing, as you will witness today. So today's topic is building with earthbags. This is an ancient building technology that is somewhat having a revival due to the low cost and low environmental impact that it has. Now, regarding the agenda, we'll have a presentation by our speakers. We'll have a Q&A shortly after the presentation. If you're watching on Zoom, feel free to drop your questions in the Q&A box. If you're on Facebook, leave your questions in the comment section. And if you're here with us today at the Mustardseed Junior School, please note your questions down and we'll answer as many as we can after the presentation. Then at around 10 p.m., we'll have a brief exercise on filling and compacting an earthbag. And thereafter, we'll do a site walkover so you can actually see the building technology in context. So here to delve into this building technology is Felix Holland, who is our registered architect and the director of Studio FH Architects, and Edson Agume, who is our registered engineer and director of Aquila Gallery.
Good morning, everyone. Thank you for coming. Thank you for finding your way out to Mustardseed. And good morning also to everyone who is hopefully now seeing our little presentation as a shared screen. As Sarah has explained, we are really focusing today on earthbag technology in this presentation. But we will give you a short background as to where we are and also as to why we are doing what we are doing. The 40% there behind me is a staggering figure, and it is essentially, if you look at the contribution of the building and construction sector on global carbon emissions, that is what we're talking about, 40%. So if we talk about the role of architects and engineers and what they can contribute to reducing the problem of, or to addressing the issue of climate change, then we have a rather big role to play. And what we are trying to do is in that context. Earth construction for us as Localworks plays a big role in how we see our part that we can play in this. You see there in the background some examples of earth construction, because there's many different applications of it. Compressed earth blocks are perhaps the most common one, the most, certainly in Uganda, quite well-known application. You see here an example of compressed earth blocks that are non-interlocking. They are stacked similar to concrete blocks using an earth mortar. Another application of earth construction is rammed earth, which is an in situ version of earth construction that relies on formwork. And then as a third example, there's earthbag construction, which is the one that we are going to focus on today. There's different, one of the key differences between the different types of earth construction is whether they are using any form of stabilizer or not. The first two examples that I showed, compressed earth blocks and rammed earth, normally tend to use stabilizer, so we refer to them as stabilized earth construction. We as Localworks, however, are particularly interested in non-stabilized applications. In many ways, you can say it is something that has followed as a natural development. We started with learning about stabilized earth construction, but the more we gain experience, the more we are interested in learning more about non-stabilized applications. You see there in the background an image of a school by Anna Heringer in Bangladesh, which is using non-stabilized rammed earth. Earth bags count as a non-stabilized application. Why is earthbag so suitable for us? We feel that earthbag construction is extremely suitable to our particular situation in Uganda, because, as we say there, it is low on carbon and high on labor. And that seems like a fairly good mix for our situation. We have many people who need work. We have wonderful soil available. And why should we not make best use of it? To give you a little bit of a background about Mustardseed before we completely delve into the technological or in the material side of it, this is going to be a kindergarten and primary school. It is a development that has been planned over a number of phases, and currently, obviously, we are constructing phase 1. We are building essentially 2 buildings. One accommodates the administration and the kindergarten, and it has somewhat of an inverted or mirrored P shape. And the other one is the primary school with 4 classrooms. In total, initially, the school will have 10 teaching spaces. There's obviously also a toilet block next to the primary block, which is going to be connected to a biogas digester. Not very much about this particular building is rectangular and straight. That has nothing to do with the earthbag technology. I want to really stress that. Earthbag walls can be straight, can be curved, just like any other sort of module-based building material. The reason that we went all curvy in this particular project really has much more to do with the educational philosophy of Mustardseed. And today is not the right forum to talk too much about it, but you can see there that our kindergarten is a rather inventive series of curved walls, creating little nooks and niches and caves where the kids can climb in. The particular importance about the classrooms for the primary school is that we have 2 very distinct sides. We have the entrance side, the circulation side, which is a much more enclosed architecture with relatively small windows and the actual entrance doors. And then on the other side, each classroom is very open and opens up to an external teaching space that is essentially some form of outside terrace that will be shaded by trees. Obviously, the motivation here is to encourage as much outdoor learning as possible. That is something that our client is particularly keen on. One of the beauties about earth construction is that the vast majority of the materials are essentially mined on site, excavated on site. This is a drone shot that we took at the beginning of the site, where we had started creating the platforms for the buildings, and where we had started stockpiling the material that is needed for the earthbag construction. And I'm now going to hand over to Edson, who will continue talking about a bit the soil capacities and soil properties.
Good morning. Well, to talk about earthbags, we need to first understand the earth. And the earth here that we use for any earth construction must be earth that is extracted from below the surface. So it must be free from roots, free from compost, free from humus, and free from all matter that is really not earth. And what is earth? What you could be able to see on the screen is that earth is composed of gravel, sand, silt, and clay in different or various proportions. Our earth here, one of the first charts really shows we dug many different holes and characterized our soil there in that chart. Most of the pits really showed that we have a lot of silt and very, very little sand, really 10 to 20% sand, and the rest being silt and sand and some little clay. And the lower chart basically shows the consistency of the soil, because the forces that hold the soil together are very important, and that's really coming from the clay and the silt particles in the soil. What I'm almost forgetting to say is that this can be characterized by the particle size distribution. So the clay is the lower part of 0.002 millimeters, and then between that and 0.075 you have silt, and between that and about 6 millimeters, depending on the standards you follow, either 6 or 10, you have sand, and above the sand you have the gravel. And the composition of this soil will determine the strength that you can get, and will also determine whether you actually can compact this soil, or whether this soil is anyway suitable for construction. And the other important part about soil is the consistency, which is the plasticity indices, which is basically how well can this soil hold together. And for our part, basically our soil was a bit on the line, which really tends between clay and silt. It wasn't really very, very good. And that's why we are actually, you'll see later that we are blending this soil to make it a bit more suitable. Yeah. The foundation, there are different foundation systems that you could use with this, but we would prefer a flexible kind of foundation system with rubble stone. Rubble is very good because it doesn't really allow moisture to rise, but it's also kind of it's a natural spring. So if there's any settlement, it is able to contain the settlement without causing damage. And it's also very good. Here we are not in an earthquake zone, but when we are building in an earthquake zone, loose rubble is quite good for that part, because it's really a natural spring to build on. For our part here, we basically have that rubble stone foundation. We have a ground beam, and we have a concrete slab. And the reason we're actually going through this, and there are series of moisture barriers within that, where, like Felix has said, we're using a non-stabilised earth material, which is very, very sensitive to moisture changes. So you really, really have to keep the moisture out. And the best way was to actually use the rubber foundation, use the a slab that seals off, and on top of that, we also have a stone DPC. On the background there, you can actually see the real picture of the buildup of this. We are using a stone DPC, which is a very hard black granite, and we are bonding it with cement mortar, and the gaps we're filling with loose sand. And this has already shown from the test that we've done that really there's really no moisture rising through this kind of material. Yeah. The mixing, we are utilizing, of course, the soil that is from the site. We've had a lot of bark excavations where we have extracted this soil, and of course the trenches. We are mixing this soil with some fraction of sand. Why we are doing this is because from what I've explained earlier about how the consistency of our soil, it's very, very hard to compact. We are looking to achieve a certain strength. We are looking at about 1 megapascal of strength in this soil. And the soil that we have from the site was not giving us that. So blending with sand was allowing us to compact it well to achieve that strength. The system of mixing soil is a bit of actually the most important, very, very difficult. You need to actually have sufficient moisture in this mix for you to be able to achieve a very good strength. We normally call that an optimum moisture content. On site, we have a way of basically, making balls and dropping them to see, whether we have either too much or too little. And basically, when you roll a ball of this earth and you throw it down, if it breaks in many pieces, means you have very little moisture. If it actually breaks in 2 pieces or just stays as a ball, you have too much moisture. If it breaks in about 4 or 5 pieces, you have sufficient moisture for compaction. It's also very, very important as you build with earth that you maintain the height of these fields and the compaction so that you can achieve continuous layers. We have tried, I can't say that we have actually done it so well, but we have managed to at least layer these bags in a way that is very consistent. Of course, if you feel too much or too little and you lay these things down and compact, you might end up with either a wider wall or a thicker bag, so you lose the layering in that way. Yeah. And we are using a bag cage. This is a flexible cage, but at the beginning, of course, we kind of measured the height of this cage that will give us a consistent bag. And every time, of course, they are filling these bags, they're actually measuring the height of this fill before they lock them. And then these bags are placed along the wall, along the profile of the wall, and compacted with rammers. These rammers, we're using steel rammers, which are about 7 kilograms. And normally you are not supposed to use force, but in our case, we have guys who have quite some energy. They are not used to just dropping the rammer. They just also add some energy, but normally you really don't, you're not meant to use the energy to ram these bags. And you ram along a line so that you actually then achieve a very a flat, consistent surface after all the bags have been tamped. A very important part of earth bag construction is barbed wire. It's very, very important to use barbed wire because you avoid slip between the bags, so it works like mortar. In brick and mortar, it really works like mortar, locking the bags together. But this also has other added advantages of increasing the tensile strength of this wall. So 2 lines of barbed wire will actually hold a lot, and we put in every course so that we actually don't have any kind of slip. So these 2 lines of barbed wire will actually achieve a lot of tensile strength to avoid any kind of movement. The other important part is the fittings, fixtures, doors, windows. How do we fit this in such a way that that they are safe and that they are not easily movable? Of course, in normal brick and mortar construction, it's very easy to drill and fix something in a wall. But in this case, the material within within these bags will not be strong enough, will not be strong enough to hold fittings. So it's very, very important that you put areas where you're going to hold, say, windows, doors, electrical fittings, anything that you're going to hang on that wall, that you allow for. There's some timber pieces that you build within, and they are basically pressed with the weight of the bags, so that you can actually easily screw a door, a window, anything there without any risks. Yeah. Yes, in this what Felix had talked about the caves, and the caves are quite some very big piece of structure, and we are actually achieving this by formwork that follows. Most of the bags that form the caves are pre-compacted, as opposed to what we had before, which you're compacting in situ and placed until they basically lock. And as you can see on those images, that's the way we're actually achieving the caves, yeah, or the arches, you must see. I had talked about the fact that you need to keep moisture out of these bags, but it is actually not very possible that you actually keep moisture out of any building material in this country. So we actually need to protect these bags, yes, from moisture, from down, but we also need to protect these bags from erosion caused by rain and wind. But more importantly, we need to make sure that the moisture that is trapped in this material actually manages to get out. And the kind of finishing that you choose for this need to allow for that. What we are doing here is that we are doing series or coats of earth plaster, plain earth plaster with some sand. And to achieve some good strength against erosion, we are actually using lime plasters, lime and earth plasters. Yeah. A bit of the labor productivity is that, from our experience here, that we have managed to achieve basically 4 workers, an average of 4 workers per day, building 54 bags. And this comes from, of course, a series of things that we have, buildings that we have done, and we have been monitoring the progress quite well. And I think the kindergarten and the admin structure, which is quite a large structure, which is about, I can't tell how many bags there are, but it's about 1,200 square meters of wall, was built in 46 days. That's where this comes from. Yeah.
Actually, I should just stay there because I wanted to ask you a question, because I had, when I explained the design, I think there's one significant aspect of the design that I didn't mention, and that is the fact that our walls do not actually touch the roof. In the cross section, you could have seen that, and of course, when we go to site, you will also see that. We have used that as a particular architectural measure to increase cross ventilation, to bring indirect light into the building, and also to really emphasize this indoor-outdoor transition that we are keen on. But I thought it would be interesting to hear from Edson, from a structural point of view, to what extent the walls, the fact that the walls are not full height and are not actually supporting a roof, how it would have been, how the design would have been different in case we had not chosen to support the roof by a gum pole structure as we have now done.
Well, I thought I wasn't going to talk about the structure design, but yeah, the walls not being able to touch the roof means that they are more like, they are working more like fence walls or perimeter walls that have no proper bracing. Of course, the roof always holds the walls together, and that would have been, structurally would have been a much easier and much comfortable thing to do, that you hold the roof on the walls so that they hold the walls together, and also the walls easily hold the roof together. So right now we just basically have two things, which is the roof and its frame structure separate from the wall structure. Not entirely separate, because we're actually using the gables or the partition walls to brace the walls, but generally the walls are freestanding walls, which makes them quite very, very difficult to design structurally, because you need quite good strength and good mass to be able to hold them away, to hold them against the wind. And the same applies to the roof. You actually need also very good strength to hold it against the wind, because it doesn't really benefit from the walls so much.
Where's the ring beam?
Well, that's why there's no ring beam, because the ring beam is normally where it ties the whole thing together, but it's also a transition between the roof and the walls. And since we actually don't have that, we have a tie beam basically that ties the whole gum pole frame together, but still has no connection to the walls.
Okay, thank you. I thought this was an important piece of information to add. I'm sure there will be some questions in that direction, but Edson, you are not actually yet fully done. We have we wanted to end our little presentation with sharing with you the challenges that we have encountered or the lessons that we have learned so far. One was already shared by Edson. That was sort of, what's the speed of construction? What can we actually achieve? How does that compare to other types of construction? How labor intensive is it? So we've tried to extract that basic information there with our 54 bags per day of a group of 4 people that we feel we have sort of achieved on average. I guess people can now use to extrapolate. We used 4 workers because this is not a type of technology that one guy does. This is really a group effort. It's quite hard manual work. So obviously you need people, and we didn't only have 4. We had, I think on average, 22, 26 people that were sort of working away and did an amazing job. A second lesson learned, and I really think Edson should explain a little bit more about that, is you know, the challenges of lime earth plaster. If you think back to my opening statement, why do we do that? Well, we are definitely on a path in this project, or generally in our work, of trying to reduce the amount of cement we are using. That is really one of the key aspects that we are interested in. That of course means generally reducing the embodied energy in our building material. So we are of course now interested in finding alternatives to a cement-based plaster. But this is not only because of the embodied energy, as Edson has mentioned, it is also really about the nature of the plaster. We want something that is vapor open. We want something that allows any moisture to move freely through the wall. The moment there is moisture trapped in a wall, the structural stability suffers. Edson, do you want to share with us a little bit about the experience made so far? We are of course still halfway through, but the experience made so far with earth lime plaster. And also how it is bonded. We've not talked much about that.
Well, for some of you who are here, might just see a little of all these samples that we have. I'm sure you're wondering what these are. But we have, from day one, we have actually started experimenting with earth and lime plasters, just because for talking in Uganda context is that I do not know personally anyone who knows how to work with lime properly in this country. So it has been a series of training the guys here, our workers, and even me myself, reading and learning these things. But what you must understand is that lime needs, working with lime is very difficult for many reasons. First, it breaks easily, it cracks easily, and this can of course be avoided by incorporating things that will deal with the tensile strength. Like we are using mesh. Some people use fiber in the lime. The same with earth. We also have to incorporate fiber in to make sure that it doesn't break apart. It holds together, because of course when it dries, it will tend to shrink and break apart. So yeah, I've said that we've done quite some trainings. It's important that we have reinforcement, and it's also very, very important that we cure these walls. A bit of a lime cycle is that the lime is of course burned from calcium carbonate to expel the carbon dioxide, and you remain with calcium oxide, and then that is what you actually use to mix with the sand and water to make the lime plaster. This can only happen in presence of moisture, and this reaction can even take for over 6 months. But of course, very important early on. And in absence of moisture, that will not happen. This thing will crumble like dust. So you have to cure these walls. For us, we are trying to do it for at least 14 days. And of course, the substrate is also very, very important. Lime is not something that is going to hold on say something like a concrete block. It will not hold there. So you need a very soft surface, which is perfect. Earth is a very perfect, it's a good surface for lime. It will bond there easily. Yeah.
Another lesson learned applies really to any building, not only to this particular one, and that is plan well, think about your services very well, and provide a lot of information prior to going on site. But the real interesting part of the picture on the right that explains sort of how the services are installed is really that, you know, there's a bit of a difference between earthbag and, let's say, a concrete blockwork wall, and that is that things are not that easily fixed to it, and therefore they need to be prepared. We have shown this before in the beginning, where we where Edson talked about how are doors, window frames, etc. actually fixed to it. Well, you need to prepare for all these and essentially insert little timber supports into the wall at that very moment. Wherever you don't do that, you will struggle later to put them properly in place. So things like built-in furniture, which we have quite a lot in this school, little bookshelves, cubby holes, they need to be thought through, and they need to be provided for already at the stage when you build up your walls. So there's a bit of planning needed. If that planning is provided for and if it's done well, then no problem at all. If not, you end up later trying to cut into the earthbag, trying to fix the supports to the wires and such things, and that's obviously better avoided. And this is an interesting one, an interesting lesson learned. When we started learning or studying about earthbag technology, we came across many books. There are many books available. One of which was for us the most informative one. I think it's actually called Earthbag Construction, if I remember correctly. And it is really a very, very good, very detailed guide of how to build an earthbag wall. And I recommend that to anyone who is interested and who wants to go that route. We studied that book in detail to understand all the challenges. This is a book of some American guys who have a lot of experience, decades of experience in using this technology. And they have, of course, used the decades to work out certain methods of how to do it. the interesting bit, the most interesting bit, or the most labor intensive bit about this technology is how to get the material up onto the wall. And you will see that later when you start doing this yourself, because you're dealing with a very heavy compacted material. These guys came up with a technology where they used relatively large tins. I think these are tins of peaches or something like that they buy in the supermarket. And I think they're about 4 kilos or 5 kilos. And they use these tins as a measuring device, but also as a device of moving earth from the wheelbarrow up onto the wall by throwing it. So there is a person standing on the ground with a wheelbarrow with pre-mixed soil, and he or she fills in the material into that tin and throws it up. And there's a guy standing at the top of the wall, and he fills it into the bag. That bag is being held up by a cage, which we have also got here on site. And they, you know, if you do that day in, day out, you get incredibly fast. And these guys, basically, they throw this thing in a permanent sort of a serial activity, probably without looking at the end, because it's just, you know, it's like the same guy, the guys are throwing bricks up a site. You can see that frequently, that they really get used to it. We try to introduce that technology on Mustardseed with our team, but we were also quite open to our team to basically explain what we're trying to achieve, but not be necessarily insisting on how it is done. And they were absolutely not comfortable with that technology. They didn't like it. So they developed their own way of working, which we have named Posho Power, because it's quite a labor intensive one, which is essentially that all our bags were filled at a central location, at that location where the stockpile was. And we used buckets to measure, or we used actually more or less our frame to measure, because as Edson has explained, it is very important that the amount of soil in every bag is very controlled, so that you get an even size of a bag. And then they actually stitched these bags and carried them to the actual site, where they then put it in place and compacted it. We shall see that in our practical exercise in a moment, how that works. But about how heavy is one bag? We don't know. 30 kilos. So it's, you know, if you do that the whole day, that is quite some energy. But, you know, our guys preferred it, and we were happy, because we all we were interested in the end is, can we achieve the quality that we need to achieve, and can we achieve a similar pace of construction? And all of this was the case. So why should we now try to enforce a certain way of building if the team on site is not so comfortable with it? This brings us to an end of our little presentation. I will now hand back to Sarah, who will lead us through the Q&A session.
Great, thank you so much, Felix and Edson. We have quite a few questions here. So someone asks to speak about termite proofing.
Well, the termite proofing here is ensured by using bags, I guess. Some tests have been done. We haven't done them ourselves, but from the researches we have read, is that put a piece of wood in this bag next to another piece of wood in the open. The other piece of wood will be eaten immediately, and the termites will not bore through these bags. But the other way of protection would be, of course, ensuring that you don't have moisture, or you don't have moisture from the ground. That's where the termites will come from. The termites will bore through stuff that has some level of moisture in. So if you have good detailing, and you ensure that there's no water getting into this soil, you should be 90% sure that the termites will not bore through. Also in the finishing, the type of finishing that you choose, lime is not very nice. It has a very high pH. Insects don't like it. In fact, one way of preserving things is just put lime.
Maybe you also mentioned about the timber aspect, how, you know, the volatility off the ground
Yeah, but for the other exposed things like even the timber, we are using timber chippings within the plaster. There we are adding some borax, and the timber we are also treating it with borax. But again, whatever even if you treat with borax and there's moisture getting in, it will still dissolve the borax, and later it will be eaten anyway. So moisture is very important. Keep it dry.
Thank you for that, Edson. There's a question here from Andrew Kamukama, who he has two questions actually. The arches, was it easy to achieve as you would in a conventional arch wall using solid blocks? And the second question is, for doors and windows, did you have to add something in the bag to stabilize the frames? A normal wall would have some kind of fishtail clamp. In this case, I missed how the frame is stabilized into the wall.
The first question was?
Arches.
Well, I'm not sure. I don't know what a conventional arch is. Arches are very difficult to build, whether with block or with earthbags. And I must say that we have done vaults, so we are doing vaults with brick. We are also doing now these vaults or these shells with earthbags. Sorry. Yes, I was saying that we are building arches with bricks, and we are also doing with earthbags, and I must say that it was much easier to achieve in earthbags. Yeah.
Just to add on to that answer, also that that was maybe one of the advantages of all our curved walls and our irregular shapes of classrooms. The amount of precision that one can achieve with the earthbags is to a certain extent limited, and that's not only the arches, that is also throughout the exact window position, the exact straightness of certain things. It helps, of course, now that we have a very irregular layout and an irregular design, where we can easily deal with a radius, say, that is not to the millimeter, because it's anyway going to be plastered with a very thick layer of an earth underlayer, if you want, so that this gives us a real chance to still sculpt the walls to the way we want. The second question, I think, is better.
The doors.
We're fixing doors and windows. I think we've talked about it, but I say that we build in some timber pieces, and these timber pieces are actually connected to a wider board that is actually nailed into the earthbags and connected with a barbed wire. So when you actually add more weight on this timber piece, you get quite some stability. So it's easier to screw or to connect anything, a door, or bit a window, into this end piece of solid timber that is actually getting its strength from another timber plate that goes much deeper into the layer of the bag.
Fantastic. And the beautiful thing is we're going to walk around, so you'll be able to see some of these things. There's a question from Rita. How does the pricing compare to mainstream construction materials, such as concrete? So cost monetarily, community strengthening, maintenance, time, and all that you find relevant.
It's great that the question already sort of indicates that the earthbag construction, the earthbag technology has a lot more benefits than just being a low-cost technology. That is really important to us. So you mentioned, or the Rita mentioned sort of the community aspect of it, and we mentioned before the labor aspect, the labor intensity. So these are all things that we are interested in, and these are all things that our client is also very interested in for this particular project. The question about the cost of this technology is a difficult one. or let's say finding the correct answer to that is a difficult one, because as I think most of you are aware, it is to a certain extent misleading to only look at a certain element of a construction and come up with a square meter rate for that element, because that element is always affecting others. So to give you an example, whatever type of wall you're using for a building has an impact on the foundation and the cost of the design, and therefore the cost on the foundation. Equally, whether that wall supports your roof or not also has a very big impact on the overall cost. I think we can give you two answers to the question, and you can pick the one that you want. One is an itemized, sort of an idea of an itemized cost, actual material and labor cost. And the other one is a square meter cost that is more derived from how a contractor looks at an overall construction project. One earth bag costs 600 shillings. One polypropylene bag manufactured at African Polysacks in Namibia costs 600 shillings. So this is number one piece of information. How many bags go in 1 square meter, Morgan? You can't remember. 0.096 square meters. If somebody has a calculator, you can tell me how many are in 1 square meter. Then you already know the cost of the bag itself. Then the material, you can practically say, depending on the site you're at, maybe entirely for free, because you may only use the excavated soil on your site, or you may have to add some sand. Edson explained that on this particular site, we were forced to add some sand into it. I think 30% of it, yeah, 30% sand. So obviously for that one, we had to pay because we don't have a source of sand on our site. And the rest is labor. And we have given you an indication of labor. We have roughly calculated that 4 guys can lay 54 bags in a day. And those are now the prime components that, you know, that you could build up the cost with. The other calculation that we have done, which is more based on a square meter rate and based on a more global view on the construction, estimates the cost to be in the region of $15 per square meter. Now, when you compare that, let's say with concrete blockwork or something else, or roadside brick or whatever, please bear in mind that we are building here walls that are almost ½ meter thick. Yeah, that is a very important, it's a very important aspect, because I feel always when different technologies are being compared on a price level, we must make sure that we compare like for like. Wilson, is there anything you want to add to that?
I don't know, political perspective. Yeah, thanks, Felix. Just to help put this in perspective, using the square meter approach, Felix has mentioned that the price per square meter for these bags was about $15. If you were to use, say, a 200 millimeter thick solid concrete block wall, that then gets to about $25 per square meter. If you then take it to a roadside brick, which, I mean, it appears cheap, but the impact is quite significant if you think about the number of trees that are cut just to make these bricks. So these bricks are at about, the local burnt clay brick is about $12 to $14 a square meter. So that helps put it in perspective.
Fantastic. Sorry. Yeah.
Mine is just a contribution towards this discussion of cost. Very often in green design, when people are looking at cost, they're basically looking at the initial construction cost of a project, yet cost should equally get into life cycle of the building. And we are often quick to find the least expensive option during construction that will end up costing the client during running of the building. So for example, no one is thinking about the heating costs at the end, cooling costs at the end, cost of maintaining the material, cost of replacing those materials. So in this discussion about cost, it is very critical for us to look at it as a lifetime cost of the building, not just the initial construction cost. And I think that is why most people have been hesitant to opt for green design. So that is just one thing we should look out for.
Fantastic. And that actually leads perfectly into the next question. What is the lifespan for this form of construction? And also, what is the maintenance aspect of the building in the future?
Well, I'm not sure I can, but earth buildings that have been surviving for thousands of years. I'm sure that it will compare quite well with any other building material. The problem with actually using cement is that with time it actually degrades, the quality degrades, and you actually have to bring down the building or whatever structure that you have used cement on, which is different with earth. Earth is the same today and it's the same 50 years. So.
I would also like to add to that from an architectural point of view, on this particular project, we have really tried to respect all the rules of the game of earth construction. So for instance, we have very large roof overhangs. So we are really protecting these walls very, very well from driving rain. Edson has explained during the presentation the triple protection of moisture from below. Triple in the sense that we first of all have a stone foundation, which in itself has no capillary action at all. We have a very dense, thin but very dense concrete slab over it. We also have a damp-proof membrane below that. And then we have this rather inventive triple layer of stone DPC, as we call it. So these are really, it's a triple action, because we are very aware that moisture is the one thing that will bring down earth construction. That's the one thing that really can weaken it over time. And we feel that we have taken all measures that are needed to be taken to make this building very, very long lasting. There was also a question about maintenance. One thing that will require maintenance over time is the lime earth plaster. Now that is exactly its strength. The strength of earth-based plasters is that they can be very, very easily repaired, improved, patched up over time. That's one of the big differences to cement-based painted plasters or chemically enhanced plasters. It is impossible to patch that up very well over time, whereas the earth-based plasters are really, really good at that.
Great. And we have a question here from Daniel, who's asking, is there a concern for rain getting on the bags during construction?
Yes, there is a concern for rain getting on the bag during construction. And what we have been doing is that after working, we cover. And we have actually been very unfortunate because from the time we started working, it's been raining until now.
Great. Harriet asks, considering the fragility of raw earth, how do these structures perform in the case of earthquakes?
That's a very nice question. I'm just reminded of the earthquake that happened in 2015 in Nepal. I think it was 2015, right? It was, I think, magnitude close to 8. And the only surviving buildings were actually amateur-built earthbag buildings.
Fair enough. Paul is asking, how can I test or check out the quality of the soil and its components locally on site from deep in my village?
Well, I would like to know how deep that village is. If it is in Uganda, it's definitely not deep in the village. Well, there are some tests you can do on site, but they're not very conclusive. And I've been so lazy because we have so many laboratories that even deep in the village in Karamoja, we've just carried this soil to a lab in Kampala and gotten it tested. But the test you could do, of course, is that there's a jar test where you can, it's very, very difficult, where you use basically the settling velocity of these different particles. You have to get a very clear, consistent cylinder. You fill it with this soil, add water, add salt, you shake, and you put it down to stand, I think for about 30 minutes, and you basically, you read, you mark where the large particles have settled, and another maybe 15 minutes, you mark whether the next larger particle, which is sand, has settled, and that basically gives you a bit of a percentage. Of the constituents. Of course, the best soil for using in any kind of construction, like I'd already said, is a gravel sandy soil, but with a bit of clay. When you have about 10% clay and about 70 to 90% sand and gravel, you have a perfect soil to build with without any kind of blending. The other thing is that you actually just build, as in you get this soil that you have deep in your village and compact it in an earth bag. You wait for it to dry and open it up and visually see whether it is stable, whether it is together. If it has crumbled, then it probably means that you don't have sufficient clay. That you just see it visually. And the other thing is that I've talked about the fact that you don't use topsoil, and the easiest way, the topsoil varies from site to site. Some topsoil could be 0.5 meter, in other places could be 100 millimeters. So normally you smell. The soil that supposed to be used for construction should actually not smell. Yeah.
I just want to add a little question to that for Edson. Would it be correct to say that if you compare earthbag construction with, say, compressed earth blocks, would it be, or rammed earth indeed, would it be fair to say that the exact nature of the soil composition in earthbag construction is less critical compared to those other technologies?
Yes, if you have the time, you can actually pack almost anything into an earth bag. Well, I'm going to elaborate on that, because if you don't have the time, our projects are time limited. You're not going to allow for this material to settle before you can finish it. It can even take a year. So you can actually pack and compact a bit, but if the material is actually not good for you to manually or to mechanically compact it, you actually have to allow enough time for this stuff to settle before you finish it. Otherwise, you'll finish it and you'll struggle with cracks, you'll struggle with a lot of things because the soil is continuing to move. But yeah, it is not as sensitive as other forms of construction in that way, if you have the time.
Great, so we're going to answer 2 more questions from Zoom, and then we'll open up the questions to the floor. Habit would love to hear your take on using earth bags for multi-storied structures.
Well, I think everything is about design. If it's design and resistance, you can actually do maybe ground +1 +2 with this. But if you're also a bit limited and you want to really go much higher using, again, earth bag kind of masonry, in a structural way, you have to look at it at stabilization. If you actually need strength, if you need a lot of strength, you can actually stabilize with cement or with lime to achieve the strength you need for whatever resistance that you need from your number of stories that you have. Yeah.
Great. So one last one. Charlotte says, thank you for setting up this and sharing your knowledge. Her question is, do you need council approval for such projects? Is the labor local? What has been your experience in terms of community participation and making decisions?
Yes, we needed the same type of building approvals that any project needs in Uganda, anywhere you are constructing. In other words, we submitted this for planning approval to the local authorities in Wakiso district, and we received the approval for it. I've mentioned before that for the client, the sort of involving the local community in the construction is very important, because this is a new school, and that school is really meant to be for the local community in this area. So the construction activities were meant to already be the first part of that community engagement and of the contact that the school, or the relationship that the school builds up with the community. So we tried as much as possible to use local labor. We also tried, this goes beyond the earthbag construction. This project, of course, for instance, it has an important element of woven mats as a ceiling material. That is actually a process that we are right now going through, where we are engaging a number of women's initiatives in the region, in the area, to provide us with the mats that we require and such things. So yes, there has been a good amount of community involvement already going on, and it is expected to increase over time.
Great, so we're going to open up the questions to the people who are here in site. I think we have enough time to answer 5 questions. So any questions?
Thank you. My name is Daniel Chanawira, and my question would be about using earthbag technology for retaining walls. If we're trying to keep the moisture out, how would it work if you wanted to use it to retain something?
Well, I guess the best answer would be, I think that whatever material you're going to use for retaining wall, you still need to keep the moisture out, right? And that's something that you could design. I am not very, very sure about using this earthbags, by earthbag meaning compacted earth, non-stabilized, as a retaining wall structure as a permanent structure. I am not sure that I have much knowledge about that. I have not thought about it. So I wouldn't want to say that it will not work, but I think we need to do quite some more studying on that to see how to make it work.
Thank you for a very good project. I noticed on the site you opted for a stone finish without mortar in between. And from your conversation about locking out a level of moisture, but also sort of allowing the moisture to get out if it enters, what was the basis for opting for that finish?
So from an architectural point of view, from a finishing point of view, actually we are not yet done. We are still intending to fill what I would say sort of an earth-based mortar in a recessed way into those joints. We are very keen on these joints. We will show them later as we walk around. I think that our masonry team is very, very skilled, and they are really doing a wonderful job in that sort of jigsaw game that you play with slates and really getting these joints very, very small. So it is an important aspect. You will also see as we go up there that in some of the corners, we are trying to use real block slates, and then we're combining block slates with slates so that there's a real, so that we also express the craftsmanship. That's an architectural explanation for it. I think it's also very interesting to talk about it from a structural point of view.
From structure, maybe protection point of view, is that we need to keep this, something that actually missed in my presentation, that you, much as you want to get the moisture out, you actually want to keep the water out also. I mean, the driving rain or any washing water that will get onto this wall shouldn't enter. And that's what we're also trying to achieve with the lime finish, is that you actually can't get water through. It's wet, it contains water, but it releases the moisture. And the same with sandstone. Sandstone is a very porous stone, but of course water will not go through. It will run over, but the moisture will actually get out.
Any other question?
Hi, I'm Tom Gruen with EMI. Edson, I had a question for you as a structural engineer. Your design for these walls, out of plane loads against the walls, trying to overturn them. Is there any kind of vertical tensile strength that you're assuming, or is it just mass and width that's kind of preventing that overturning?
The curvy nature of the walls was actually meant also for structural reasons. So we are using shape, we are using mass, but we are also using some level of compression strength, really not tensile strength. I mean, the compression width within that, of course, with the highest storm or wind you can ever have, should not crush the material. And I think from, I don't remember the exact figure, but it was extremely low. I think it was really coming to like 0.1 megapascal or something. Very, very low, that could be resisted with anything. Of course, because of the shape, when you put in the shape of the walls and the size and the mass of the walls, it actually reduces the need for tensile reinforcement.
Great. Any other questions? Okay, so we are going to answer some Facebook questions. There's a question from Timothy Michael Machivi. With construction being a back and forth process, in the event that you have design changes and have to essentially move walls or cut away some walls, how friendly is this to demolitions and reconstruction in part?
Very friendly. Very friendly. I mean, it's not only very friendly to changing a wall here and there and removing something and adding something, it is also very friendly to disappear altogether. That's one of the beauties that we, I think Pamela sort of, mentioned it a little bit. The recyclability of this building of this technology is amazing. If you just leave it there and do nothing and remove the roof, it will disappear and become a farm over time again. So yeah, it's a very flexible and easy to use building technology.
Okay, another question from Aaron. Given the texture of the sacks, how do you apply finishing to it? In other words, is there flexibility when it comes to surface finishing?
Well, quite an important question actually for all of us. It's impossible to have any adhesion onto that material. It's very, very difficult for anything to hold on. So during construction, we're actually building with galvanized wire through, where which we use to tie the mesh that actually hold whichever kind of finish that that is going to come. But you cannot really rely on adhesion to this. But what I've seen other people do, they also melt the bags, and then you can actually have proper adhesion onto the clay, onto the earth. Yeah. But
so just to add on to this, you may recall the photos and the drawing that showed the barbed wire, the 2 strands of barbed wire that are in each course. We have at a certain spacing, we have added to those strands of barbed wire, we have added binding wire that we made stick out on either side of the wall. And with those binding wires, you then fix chicken mesh, very ordinary galvanized chicken mesh. You fix that, and that is what then provides the basis for the plaster. I think this. I saw there's actually a question coming that is very similar from Clemens regarding the finishes, the possibility of the finishes. I think that sort of answers the question. We would not necessarily recommend to leave the earth bags exposed and do nothing about them, because they do degrade over time. They are, they will not withstand forever the UV, for instance, the UV exposure. So some form of finishing is definitely recommended. In addition to roof overhangs and good protection from the ground and etc. But I think it is an important aspect that Edson just made. It is quite interesting to understand that the polypropylene bag itself is not what gives this technology the structural strength. It is more, the bag is a type of formwork. It's a type of almost temporary formwork that allows you to compact. But once the compaction has happened, and once the material has dried out, the strength itself is not coming from that bag. Therefore, some people actually remove it and melt it away, and then have a proper earthen material to deal with.
Great. So one last question. Planning challenges by O'Malley. Planning challenges. Is there a standard size of bags to use?
well, I guess you start by designing the size of the wall you want, and then you you go in for the format of or the size of the bag that you want to use. The bags that you'll get on the market are either too small or too big. I think we tried with 50 kilogram sacks, which gave us very, very wide walls. And then we tried with 25 kilogram sacks, which again gave us, couldn't build a wall because they are too small. So what then we did, we just worked with the factories and gave them the size of the bags we want, and they produced them. But it's determined by the size of wall you want to achieve.
Okay. Because Felix is very particular about carbon footprint, did you opt for sisal bags versus the plastic bags? Have you ever been very particular to ask for the source of the plastic, And then also, how would you have compared this, for example, with a plastic bottle filled with earth technology?
No, I think this is more of a structural question. The sisal versus the polypropylene. But, I find it always very important to find the right balance, and to there's nothing in life where there's no sort of black and white, and there's always a bit of shades of gray, and there's always a middle path that one needs to be taken. So I feel that of course we discussed it. What's that plastic like? Where does it come from? Who makes it? How is it made, etc. The proportion of it within the entire wall is still absolutely minute, and it is locally made, which is very important for us. We have actually, for this entire project, for anything you see there on the side, not one bit of material has been imported into the country, including these bags. So to a certain extent, you can also see the positives in there if you engage the local factories and you generate employment. I think Edson should respond to because I asked exactly the same question, of course. Can we use sisal? And why not?
Well, we actually wanted to use sisal, remember? what actually the biggest issue with SISO would be biodegradation, which we could have solved again by probably soaking them in some borax mixtures. The other was the cost. They are I think 5 times more expensive, and I think that's what killed the SISO was the cost.
How does it compare to? What's your question about the recycled bottles in terms of but in terms of structural strength or?
Well, I know nothing about recycled bottles. I'm not going to lie about that.
We shall try that out on another one.
My question is about the shape of the structures. I realize you people adopted non-irregular walls, which is advantageous to the stability of the structure. Yet if you realize Ugandan construction is more of linear walls, and don't think this is what people are used to. So at what disadvantage are the Ugandans who like the linear walls at, especially when using this technology?
Well, I must say that if you have a roof over that is holding these walls, I don't think the shape should be a limiting factor. For us, we are almost trying to build a perimeter wall, and that's why, structurally speaking, the shape was very interesting for structural stability. But I think if you have a roof frame tying all this together, you can easily build linear walls without worrying about anything.
When we did our research on earthbag technology, there's a number of buildings you come across that don't show, you wouldn't tell that they're made of earthbags. They are rectangular buildings, contemporary architecture, plastered and finished. So the only distinguishing sign is that the walls are very, very thick, which is of course climatically a wonderful feature of a building.
Okay, one last question.
Hello. So I wanted to ask, is there a minimum thickness of the wall required? You know how we're used to the 230. When I'm guessing, since here we're using sand, and you need a required weight to sort of keep the wall standing. So does that make the wall thick, and wouldn't that take more space? Okay, I'm trying to see if most of the time, like you want to use earth, and you want to build the house in the slum, there's little space and stuff, and guys want to use this because it can involve them. So is there a minimum thickness?
I would say that there's no minimum thickness as per se. Even the 230 you're saying is really not a minimum thickness, but for practical reasons of compaction in situ and stuff, you are really not going to do a wall thinner than 300. Yeah, for practical reasons.
Yeah, fantastic. So keep the questions coming, keep noting them down. We are going to go into the next exercise, which is filling and compacting an earth bag, but keep the questions coming because we'll answer them as we do the site walkover.
Are we filming this so that people can see it?
Yeah, we're going to keep filming this. So if you're watching virtually, you can tag along.
We are trying to fix the problem with the camera. I hear that you guys are not seeing us, but only hearing us.
Now, since we put sand on top, now we need to mix. We need to mix sand and the soil to get a uniform color. So let's mix, bring this side.
We're not going to pay you.
Yeah, you can mix like that. No, it's okay. You first mix like that, then you bring this side. Yeah. this one on top, like that. Okay, let's move it this side. Put this side.
So we have still the problem with the camera, so we need to describe what the guys are doing. They are now busy mixing in the ratio 3:4, you said?
Yeah, in the ratio it's 3:4, yeah. When we are mixing, we should make sure what we are pushing this side should be separated from the other one. So should be a gap in there.
But you're not yet done, you will still have to fill. Good news is we don't have to carry it to the side because the side is right here. We hope that the picture will come back to the Zoom session once we start moving again. In the next part of the program, we are going to move around a little bit and show the buildings, and I hope that that will then work again. In the meantime, we are filming and recording, and some of these images will hopefully be available afterwards as a recording.
I think we are almost done now. Now what we are going to do, we are going to test for moisture content, or what we really want. What we can do, maybe you carry a little bit of the mix in your hand, you press it. After pressing it, maybe at a certain height, you can throw. If it doesn't shatter so much, then I think the moisture content is not so bad. Or maybe if you carry this and you squeeze it, water through your hand, then that means there's a lot of water. So maybe on that, yeah, maybe we need to squeeze it a little bit more, because mine was not really breaking too much. Yeah. Maybe Edson can also talk more about that. And
yeah, basically what we already talked about, the optimum moisture content is if you roll a proper, with some energy ball, and you drop it from about a meter. If it shatters so much, then you actually don't have much moisture. If it stays together, in my view here, it looks like we might do a little bit more.
Maybe we need to mix again.
For these testing purposes, maybe that's
no shattering much.
Well, the expert says that it's enough.
Now what we are going to do, I think we are ready now to get, this is a bag stand. This is a bag stand. I think one of our guys is going to demonstrate how to do it. So you can start. Okay. So is going to show us how he's going to put the earth bag in our bag stand,
which is a little bag stand that is made out of two rectangular sort of two flats that are bent in rectangles and joined at the middle so that it forms like an X. And we are now wrapping over the bag in such a way, I think, that it exactly touches the ground, isn't it?
Yeah, that's true.
What is he now measuring?
Now he's trying to measure the size of our bag, the
What
height
height
of
are
the
we?
barrel.
What height are we trying to achieve?
We can try to achieve like 60, 57 to 60 there.
Okay.
Then we have buckets which we use. It's going to fill the bucket, then
Why do you use buckets?
it's easier to carry.
It's easy to carry, but are you measuring by bucket or you're measuring until the bag is full and has reached the top of the stand?
We are measuring up to the height we want for the bag
So
stand.
the buckets are really just a carrying device. So the guys are now filling these buckets and now pouring them into the bag. How many go into one bag? 4.
In fact, also they help, like if you want to maintain the uniformity, that height there.
That first bucket already into the bag. So it is not just a matter of pouring it into the bucket. It is also about already pre-compacting the material into the bag. Now comes the second bucket. Any volunteers, you can now please join in. Don't do all the work for them. They're here to do some work.
Then after maybe putting 2 buckets, then you have a little bit pound.
Now the second bucket is now already actually being tamped with our steel tamper, so that the compaction is already being increased. Okay, I think they want to finish themselves. The next one. Okay, the next one. You're going to do the next one. So that's the third bucket. Again, being tampered with the steel tamper. And now the last one. I can now hear that the picture is back. Maybe MTN has recovered, and you can again see a little bit. Here you can see the final bucket. What's the next step?
The next step is to pull what you had covered on the bag stand. Then
now we're opening the stand, and now it is about closing the bag correctly so that the material doesn't fall out when you carry it to the site. For that, they are using small pieces of binding wire, is it? Galvanized wire, which are pre-bent into U shape. I think in the beginning we used something else.
We are using nails, but it
was quite a costly thing.
Yeah.
And then we came up with that solution as a much more efficient solution.
Yeah, that's true.
What's next?
They are locking the top part. Then after, he's going to remove the stand. Then it tries to be so that it bends this.
The corners.
The corner.
That is what they call diddling, is it? Because we don't want these corners to poke out of the wall later, so they are now effectively emptying them and then wrapping them around so that they form a nice clean corner to each of the bags. I hope you're learning, because you have to repeat all of this in a moment. And we shall test the bag. Yeah, diddling is I think it's a word that these guys invented who wrote that book. You should really read that book. It's fun. It's fun. Yeah. It's fun to read.
Now our one bag is done already. It's ready to be placed on our foundation.
But I should also mention that, for instance, the diddling itself, they do it differently. They actually wrap in the material. They don't actually use stitching or any kind of nail. So we are placing it now on the stone foundation. And what are we now doing? Are we filling the second bag or are we compacting? We fill the second, 2-3 bags. So can we do this concurrently? Can one bag be filled by some of the visitors, and can 2 other bags be filled by our team? So that we have a bit to compact.
Use one. Bring the other one.
If there are other volunteers, it doesn't only have to be the same people. If there are other people wanting to get their hands dirty, now is the time. Yeah, you fill the bag. Somebody else puts the bag over the stand.
One can be used here, another one.
Any more volunteers? Well done, Pamela. First bucket goes in.
I think let's not press it. Let's not press it. Just make it level. Then we put it there.
Do we have a third stand, or we only have two? We have a third. Okay. So team number one is definitely ahead. Team number one is already filling the second bucket. But somebody now needs to compact team number one. Jump it a bit. Team number two is far behind. There you go. Albert is now. Do the bags.
How many packets there?
Two. Now you first need to compact. Does the bag ever rip when you do this, or does it ever happen that it breaks? They are so strong they don't break. Maybe that's another reason why we didn't use sisal. Okay. Pamela's team is almost done. That's the fourth bucket, is it? Or is it the third? That's the fourth. Okay. Now let Alba do the job of closing. Yeah, she watched very carefully. I can see it. You can have a job. Pam, you can have a job. A bit of expertise needed there with the U nails.
First to make it tight. Try to pull that thing.
So Pam, you're only 53 bags to go, then you can go home. Oh yeah, sorry, yeah, you're only filling it. Yeah, you also have to place and compact them. Uh-oh, team number two has overtaken because they are done. I know they still need to do they need to diddle the other side. which again is about tidying up the loose corners. Okay. They are struggling with that thing. I hope once we have these 2 bags ready, we can then put them in place and start actually compacting. Other side. This is a hands-on workshop. Why is it important to diddle the corners? Why do you mind so much about the little poking out bits at the ends?
Well, because if you don't do it, the bags develop ears. When you're plastering, they don't give you a good surface to plaster to.
Okay.
Yeah.
Now we have placed these 3 bags very close to each other, and they are now being compacted. Maybe some guys can first show it, and then some volunteers can try to.
Maybe one thing to understand is these bags should be close to each other, should be tight. So if they are not tight and you leave there a gap, that means they are going to increase in length. And we want to maintain the same height we measured there. So I think that's very important.
Okay. All right, let's go. Now you will see by how much the compaction will still happen.
You have to do continuous. As you compact, you have to do a continuous line, not one by one, so that the bags go down evenly. So.
Okay. Any volunteers who want to do a course? So of course, according to Edson, the theory was that muscle power is not required and the weight of the jumper is enough, but we'll see. Somebody else? What is our target height for the bags for the course?
Should be maybe 130 to 140 there.
And do you then regularly measure?
Yeah, we do measure, and maybe we try to put a level on top and check our levels.
How often did somebody actually hit his own foot?
That's it. Yeah.
It's rare.
Does it happen?
And when do you know? When do you know that? When do you know?
You want to try? You want to try? You do. No, there's more. They want to. We have a volunteer here. Very good. Don't hit your foot, please. You are live on Facebook.
How high are you supposed to drop it? Well, wherever it's Yeah, I think I asked just how when to stop.
There's the sound changes.
That is an interesting information that the sound changes once the compaction has been, once our target compaction has been reached. It's now the sound, is it, or not yet? Woo!
Yeah.
That is the one we are looking for. Not that. Ah, there you go. And that is a sign that we have reached the levels of compaction that we're looking for. And if the quantity was measured correctly, then it automatically also means that we have reached the correct height of the course. That one is not yet ringing. Okay, it is. So Geoffrey, what's the next step?
The next step is to align these bags. Since we have a foundation and we are looking for a straight line, a straight wall. So we need to put on level and make sure they're in the middle of the foundation, which now these guys are doing.
And then comes the barbed wire?
Yeah, we are supposed to put the barbed wire on top. We've already arranged. We don't want that barbed wire. Once somebody as you pull, it rolls. So just pull and.
So a bit of alignment of the wall going on now. The luxury of the string you didn't have with all those curves, though.
No.
The first straight wall you're building in the whole project.
Now maybe what we can do is to maybe stamp a bit since we are moving and all that, so that it comes tighter again. Slowly.
By the way, any questions while you're watching? This is also a good opportunity to ask any further questions. I don't know whether anybody sees questions that are being asked online, but the ones on site we will certainly hear.
Slides around more than other courses because of the lack of the barbed wire.
Yeah. The first course is actually quite difficult to do. You have to set it and it keeps moving.
Yes. Can we now we see how they remove the barbed wire from there. Obviously without any gloves, as you would expect. It's not like we don't have gloves on site. Very nice leather gloves. Edson, would this technology work without barbed wire as well?
Well, it would work, but there's a risk of these bugs slipping from
the surfaces are quite smooth. So
during construction, or you mean
even
afterwards,
afterwards,
in terms
it's,
of
it's something
wind,
that when you have
earthquake?
any movement, ground movement, whatever it is, it's slipping happening, they really you need this barbed wire to ensure a proper shear strength. And for it to work as a unit.
Edson, there's a question here. Why is there not also barbed wire below to somehow stabilize it towards the foundation?
It has no effort.
It wouldn't really hold the stone.
This holds because now another bar comes and goes. But anyway, all masonry buildings have that with design where the PPC is basically you can move it away. Like, yeah.
The GPC, because GPC layer of stone, where does it?
It would have now been in between. We've now basically not done it in this sample. We would have normally, obviously this is just a single layer of stone that was just mimicking a foundation. Actually it was 1 meter deep. And then came first the slab, and the slab sits on top of the foundation. Yeah, the concrete slab. Then come the 3 layers of stone VPC. Then we start with the earth. So I think that's also another aspect. This is of course a single layer of stone laid in a bit of earth. Of course,
we
it was.
did this not to mimic anything, but to just provide a flat surface to compact against.
But what I'm trying to say, in the buildings, the triple layer of stone DPC was a lot more stable because it was actually in a mortar bed, so it wasn't wobbling that much as what we've seen now. Geoffrey, are we also now under normal circumstances, you would have also fitted your binding wires now, in order to then later help us with a plaster?
Yeah, we are supposed to put wires which can help us when we are plastering.
You have them here?
Yeah, we have
there they're coming. Wonderful. What spacing do you use in length? What spacing do you use for this?
I think we are using 400.
Every 400. Okay.
So there's a question here from Iva, I think regarding the barbed wire. Is there a particular number of earthbags that the wire should run over?
From Iva. Hi Iva, how are you? There's a question from Iva as to whether there's a particular number, a minimum number of bags where the binding wire needs to run over, or can you do this in the barbed wire, sorry.
I don't understand it.
Well, right now it's holding 3.
All the way.
No, it goes all the way.
Except for where there are doors.
Yeah. It looks even on the door thing. Why don't you demonstrate the doors actually?
Geoffrey, can we see how you put the doors? This is it sort of got lost a little bit in the presentation, but there's this so-called Velcro technology. Edson, why don't you use this opportunity to explain the Velcro?
We are only doing 2 courses this side, right? So we'd rather demonstrate it now.
This is now a demonstration of how, say, a door or a window or anything else is being fixed in to the layers. You see this sort of L-shaped wooden pieces. Edson explained that before. The same guys who invented the term diddling also called this Velcro. This is just being now held in place by a bit of nailing, but actually it is a gravity, the pressure of the following courses will actually hold it in place. And then I think they have placed it flush on the door opening so that later any type of door frame can be easily fixed. What are we doing there in the middle, Geoffrey? What is the middle one for?
In case we have like an MK box, then we can fit it there.
So for an electrical socket, or for for our built-in shelving, or for our cubby holes, we needed a number of these supports so that we can later easily fix any type of furniture to it or fitting. You guys should be filling quickly, so because we are running out of time, so that we can quickly demonstrate the second course as well. I hear we have only 5 minutes left to conclude this exercise. But I think what we can do, that will be enough to see one more bag being added to it. And if we want on the way over the site, we could still pass by here at the end and we see the exercise concluded.
Okay, so we're going to answer some questions in the meantime. Thank you for this initiative. How do you imagine a future with earthbag construction in Uganda will impact the amounts of soil excavation? Lastly, what happens to the environment from which the soil is excavated?
Very good question. Uganda, of course, is in almost all cases, you find that you end up on sloping sites. We rarely work on flat sites. Very, very rarely. I can maybe recall one site that I worked on that was really flat. So we are normally always in a situation where we try to create platforms for the building, and that is the material that we are now utilizing for the walls. We actually, right now where we are standing around this tree, we used to have a huge mountain of excavated soil that we kept dry with these orange tarpaulins, or try to keep dry as good as we can. And this material has practically gone. There's a small heap there next to us left. So we are really happy that we have managed to estimate the cubic meterage of walling so precisely that our building levels ended up working out really, really well with that. We are in a situation where we have not carted away any material at all. And the little bit I think that we did cart away, we just carted to the football pitch where we had a bit of a need for additional filling. So in that sense, my first answer would always be try to use the material that you have on site and try to dimension it correctly so that the building level essentially is being chosen smartly. What are we doing with the areas that we have excavated? We are of course now going to plant it up. This is going to be an incredibly green school. We have kept all the vegetable soil that we had to first strip. We stockpiled it on the lower side, and we're going to spread this out, and then we are going to make this the greenest school you could possibly imagine, so that we are not faced with erosion issues or anything like that.
And while we're still here, another question from Rukundo Peter. How do you reinforce the corners and opening edges, and what provides resistance against overturning of these earthbags in case of any horizontal forces against the walls?
Well, the corners are bonded like any masonry corner. Of course, with overlapping barbed wire. It's quite difficult for you to push over this wall because of the weight. So that's the stability mechanism here, is the weight, and which is the same for all masonry buildings. You're basically using the weight and the shape.
So we're now going to do a site walk around, and we'll come back to view this experiment when it's all done.
Now, what we have learned in the past is that when the phone that we are using to broadcast this event, when that phone ends up walking into the buildings, the network tends to go very weak. So we will try to stay outside of the buildings, or those people on site can of course go in, but we'll try to keep the network going. As I said before, if it doesn't work out, we are recording all this and you have a chance to review some of the parts that you may have missed. My proposal is that we are now going down. We are starting with the building where the earth bags are most visible, and that is the admin and kindergarten section. And then from there, we walk up the hill to the primary building and also to the toilets. The kindergarten is designed as a courtyard building. Again, with that idea in mind that we want to have as much as possible outdoor teaching, playing, etc. And given that these are very young children, obviously there's always a need for controlling in and out. So a courtyard was obviously was an obvious choice. While we are here, maybe it is also important just to briefly talk about the columns and how the V shape of the columns. I think we had already explained that the roof itself is not actually supported by the columns. Sorry, by the walls. The walls do not touch the roof. It is the columns that do the majority of the work. Only some of the partition walls, those walls that are essentially separating the classrooms, those walls will go all the way up, but not in earthbag. That is actually a timber frame that will be clad with the same material that we use for all the ceilings, which is a woven mud. And that timber frame that goes all the way up is doing the bracing of the building and connects basically the roof to the structure. So the earthbag, our entire earthbag construction is finished. We are no more building any earthbags. We are done. That is the final height. The V shape has many reasons, including that obviously a slightly tilted shape is a very interesting way of bracing a building. So we actually needed no additional bracing. You will not find any X's or diagonals that hold it, that stiffen out the building in either direction. One more word about the eucalyptus is also that an interesting aspect to this project is that we have excavated for a large playing field at the bottom of the site, and that area that we found there had a relatively young eucalyptus plantation, and we cut all that eucalyptus down, not all, but most of it, everything that fell within the football pitch, and we utilized all of that wood for the roof structure, not for the columns that you see. They are too thick in diameter, but you see down there where the guys are just now starting to build the roof, that those thinner profiles are actually, most of them or many of them are harvested on site. So that again is another way of really keeping the materials on site. I would suggest we move down and we have a bit of a close-up look of some of the earthbag walls, also maybe the DPC detail. This is a typical kindergarten room, if you want. Side that is relatively 2 double doors, glazed steel double doors. In the primary school, there will be 3. And then, you know, I mentioned this before, of course, the idea being that as much as possible happens on the outside as well. And this is combined with a very large roof overhang. You can see how big that space is that is covered, and that hopefully will reduce on the need to be completely indoor. If you look around the corner there, you can see one of those caves that you have mentioned. This is of course just a little playful element of these kindergarten classrooms, allowing the children to climb in there and hang out there, play there, etc. All of the kindergarten rooms have at least one of those. And the other aspect obviously is to mention, you notice that these rooms are not rectangular. I said that before during the presentation that that aligns very much with the client's philosophy, who wants to enable a teaching that where not everything is in a traditional frontal way. They want to have a big variety of teaching styles if possible, or at least a space that enables that if the teacher so choose. There you go. And it's these caves are going to be finished exactly in the same way as all the walls, which is this very, very smooth earth plaster. We have some samples down in the contractor's compound that shows you. It's sort of a very natural earth, a steel troweled smooth finish. The experiments we have made so far, the question is whether it will be sturdy enough. The experiences we have made so far with the lime earth plaster samples is that they are immensely hard, strong. What we will not do is sharp corners for that reason, because that is always what breaks out. But this also works extremely well with this language that we are doing here, that sort of very smooth language. So we will curve everything. You will also notice that these wooden window boxes are protruding out. That's another way of protecting the plaster edges and not having any exposed plaster edges, actually. These little window boxes will all be colored. So, Mustardseed has a certain color scheme, and we are picking up on that arrangement, randomized arrays. In Sentema, sort of fixing devices, because in this area we are going furniture. These are in a certain stepped way that the kids can even climb on them and such things. So it was very important to fix them properly to the wall. So this is how we did it. Maybe one word about the floors spread out. To protect it, we have a essentially dense concrete slab, and we ground it down so that the aggregate is exposed. And it turned out very, very beautifully. In the moment, it's hard to imagine, but by the time when we are done with the primary work, by the time we can remove this protective sand, we actually only need to go once over with a polishing machine, and our floor is finished. Very sturdy, very long-lasting exposed aggregate concrete finish that we find with this application that also really expresses the material that is used in a very nice way. Edson, there's a question here for you. Whenever the questions get difficult, I call Edson. Why is there a vertical continuous joint in the corner? Why is this not bonded well?
Well, we need to explain it from the outside, because this could be just the field. But the wall on the outside is bonded because it's quite a massive piece of the wall. I actually don't remember plan design, but from up there you can see the edges actually bonded in. This is just massive, the massive.
So the architecture is such that the wall thickness keeps changing. You have a curve on one side, and we have always, of course, made sure that the primary structure is running through and bonded in, but there are at times, for instance, here is a thickening. This is not the structural wall. The structural wall is on the outside running past, and this little corner is actually only there because this cubby hole fits into it.
But again, also the barbed wire helps it holds it because the barbed wire always crosses.
Okay. Okay, I think we move. If you have any questions, you can keep asking them as we go. I propose we move up towards the primary block. This is a good area to study the our so-called stone DPC. I don't know whether everybody heard the explanation that Edson made at that stage, but this is a very hard granite, local granite stone that we have applied there in 3 layers, 3 thin slates, sometimes 2 if the slates are a bit bigger. And the important part here is that obviously the primary reason is that we don't want moisture to rise through the wall. And the way we've done it is that we've placed them in a conventional mortar bed, but we left the joints, the vertical joints between the stones, we left them free of any mortar and instead filled sand. Sand obviously also has 0 capillary action, and therefore we are completely sure that on a triple layer, we have avoided any risk of moisture moving up the wall.
So there's a question here by Natalie. How is curvature achieved in this construction?
Yeah, this is a good question. We can just look there where there's a nice curve. Because I mentioned that before, it is not at all the material that forced a curving shape. It is the other way around. We wanted curved shapes and made it work. It is achieved like in any other brick or block-based material. Essentially, these are faceted curves. What plays in our favor is that there is so much earth plaster finish going over it that can be very, very thick if it is applied correctly. That eventually we will have a perfect smooth curve. Okay, let's move up to the. Maybe we quickly pass by the area where the mezzanine will come. There's one area where we are using the height of the building to add a small mezzanine floor. Entirely out of wood.
That's true. It has been quite fast in the end.
This is the admin section of the school, and there's of course a need for offices, and there's a library, and the library needs a store, and the main office needs a stationery store, etc. So we ended up proposing a mezzanine floor, and that mezzanine floor, the support for the mezzanine floor, you see there, it will eventually not be visible. But Edson, I would really like to hear your explanation here, because you responded before that you could build multi-story buildings with earthbags, but even just for a mezzanine floor, you put in gum poles as a primary support. Why didn't we just place the mezzanine on the earthbags?
Well, this kind of earthbags, the way we designed it was actually not meant to carry more floors. So we wanted some level of consistency, and this is just a small area of the building. It didn't make sense to reinforce one part and then go. So just for consistency, we just decided to build in a structural frame. So.
And I think you also said that it would need stabilizing if you wanted to go multi-story, which we didn't want. So this detail shows it quite clearly how we've done it. In these cases where we need vertical wooden supports that are not there to support the roof, that are part of the wall, we have these steel brackets of these walls. Here we are going to span across here with relatively big laminated eucalyptus members that support the deck. There's actually in the whole school, there's only one type of wood used, and that is eucalyptus. We have decided not to use anything else because we feel that this is, you know, with all the negative biological or ecological sides to eucalyptus, it is still, in our view, the most sustainable timber to be used in the local market because it is planted in plantations. Many of the other timbers that are available locally are not from proper plantations and therefore are normally illegally cut. Now we are going to move to the primary block where you can see a little bit about where you can get a feel for the roof.
Circular details.
Again, I think Edson would be the better person to answer this. Edson, what is the reason that we used the gumpo lintels? What's I don't know whether there's, we should probably show it while we're talking about it.
The design actually has sawn timber, but the guys on site thought fit that the gumpos will work better, and we had them in printing. So they also match the sizes of the bags. Whatever they use have to match the layering of the bags. Yeah.
So it is actually, it worked out really well, and it was a detail that was done on site. We had shown sawn profiles that are on top of the windows, and then you know, we had a lot of offcuts. They work exactly with the height of the bag. It is an ideal adaptation of the design, I think.
Eucalyptus has a tendency to warp over time or to split up. You cater for that in the door and window frames.
There's two answers to that. One is that we have really insisted on this wood to be dried, kiln dried before. And the other one you can sort of see. These are actually very, very small members that are laminated together, glued together. And in many ways, the smaller they are, and the better they are connected to each other in an alternating way, in a staggered way, the better you address the problem of cracking, of warping, and of all these things. We are working together with somebody who is really experienced with eucalyptus, and that is the reason why they don't warp. There's a certain roughness built into the design as well. As you can see, that's of course now the advantage of this type of design. There's a certain amount of roughness that we are happy to accept as well. This is not sort of the most refined joinery that you need, but if I show you later our door shutters that we have already on site, they could go into any hotel as well. They look really, really beautiful with recessed joints and very good carpentry. So it is a bit of a myth that eucalyptus is an unworkable wood. That many people say that on the local market, that you can't do proper work with it. It's not true, but people tend to use eucalyptus that has been cut yesterday and been, and is totally young and wet. No timber is usable when it's
I have two questions. One is about this. Yes, that drip. What's the purpose of that drip? Second question is about eucalyptus. Did you think of other options like bamboo? Yes.
The drip is there because you will have in this particular case, we will have the glass louvered windows, and the lowest of the louvers will end exactly there, and we have a very small fall here, and we'll deal with water. That said, don't forget that we have a 2-meter roof overhang, and that we really do not expect a lot of water here. But that is the primary purpose of this. There's also a drip down here, so if there is any water in a controlled way. And I did, of course, dream of bamboo. This, in many ways, the aesthetics of this building is that of bamboo, and we will see that if we go to the primary block. The way we have done these scissor trusses, you could just do it in bamboo tomorrow, and it would be much more lightweight, much more efficient as a technology. There's two primary reasons why we ended up not using it. One, we were not convinced about the supply yet. We know that many people are in the process of planting bamboo, etc. Two, to be very honest, our experimentation, our thirst for experimentation had been quenched on this project at the time when we had worked on stone foundations and earthbag construction and wall and roof not being connected and lime earth plaster. At some point we felt we need to reserve some of that for future projects, so as also not to overtask the team with all these levels of endeavor. Let's go and have a look at the roof structure. When we designed this school was the idea that we want to create a school that feels like a home. I find this particularly sensible when you deal with relatively young children, primary school, kindergarten, etc. They spend, this is a day school, this is going to be a day school, at least for the initial phase. They spend a lot of time of their day in this school, which they're not at home. And some of these children also don't have necessarily a very well-established home. So a school can actually play that role to really provide that sense of homeliness and of warmth and of embrace and protection and all these things. And I find if you just look at this little entrance, it really does feel like a little house entrance. The roof is a roof like a child would draw a roof. It's not something else. It is not something mono-pitched or flat or anything. It is a real roof. And each classroom has a little, a little entrance area, like a little porch almost. And then you have these little tiny windows that really provide almost a bit of intimacy. The roof will not remain from the outside as it is right now. What you now see with this metallic roof sheet is actually only the first layer. There is a second layer over it, and that layer is, in other words, eucalyptus offcuts. We are actually exposing the bark side to the outside, a little air gap. And that is largely intended to, address some of the weaknesses that metal roof sheets have, such as noise, such as radiation heat, and that was also important for the clients, the industrial look of it. Obviously, by using a natural material on top of it, we are going to have a much more friendly, a much more natural appearance of the schools. And from from inside, a woven matte ceiling throughout. Notice these very many translucent strips that we have inserted into the roof. They will be eventually much narrower because the eucalyptus offcuts will protrude over it if you want, and only leave a very small gap. Essentially, one of the offcuts is missing, and that is where light will enter, and that light will then again be filtered through the mat. So there will not be as much daylight as there is right now in these rooms, but there will be a small amount of filtered direct light in the classrooms, which in our experience, if it is small enough, works really, really well without overheating the building. That's obviously the danger that you have if you put too many skylights in, you overheat the building. But if you just enter, you will feel that already now there's a remarkably comfortable climate. This is surprising. In my view, number one, the roof sheets are, and number two, ventilation, because the walls don't hit the roofs. Obviously, there are big openings, etc. And then we have these very heavy masses of the earth wall, which clearly also generate a very comfortable indoor climate. So we are quite confident, right balance between a very good, still a very cool indoor climate.
So there's a couple of questions here. The first one is Ivor again. Is there any finish applied on any of the timber or anywhere around that? Preservation method.
Yeah, we have dipped this timber in a borax solution, and I think also maybe before handover we'll reinstate that by spraying. So that's the preservation we're using, but we're not sealing anything.
Everything else that is not dipped in borax, which is external, everything else is going to be treated with linseed. Bringing to a question that you asked, is so magic about borax, why don't we just use that green stuff, whatever it's called?
Well, I hear that borax is a bit more eco-friendly, not so poisonous like arsenic. Plus, if we have to deal with any kind of arsenic, we actually need so many approvals to actually even buy this stuff, even if we are to allow to use it. It's extremely hazardous. Borax is natural and it's a good thing for, and it works quite as well also, because both of them are soluble in water, and that's the biggest issue, because when water gets in, this stuff dissolves and you lose the treatment at the end of the day, whether you are using arsenic or you're using borax.
The second question is from Natalie. Won't the small size of the entrances to the classrooms hinder movement to the children in and out during rush hours, like break time and lunchtime?
Well, yeah, they are not that small. They are normal. They are like any classroom door tends to be a normal room door, 900 wide. These are also relatively small classes. We're talking here of maximum 30 children. And then, as Pam just mentioned, of course, we've got on the other side, we've got 3 double doors that are fully openable. So if somebody feels that the room entrance door is too small, then they could always use the side that leads area. So I'm not concerned about that. I think this is sufficient.
And a question from Kwagala Juko. The eucalyptus offcuts on top of the metal roof, what shape are they and how will they be attached?
I can definitely see that you guys are following online. That's great. So I mentioned that there is an air gap. So in other words, the eucalyptus offcuts do not actually touch the roof sheets, meaning that there's something in between. What there is in between is a thin eucalyptus stem, a 50 mil diameter, a member that runs essentially exactly on top of the purlins. every other purlin, sorry, every other purlin. Now, how is that member fixed? That member is essentially fixed on a small steel angle, and that steel angle is welded to two small pipes that are spaced out in such a way that they are resting exactly within the valley of the corrugated sheet. Thereby, we are avoiding these angles or and we are also going to fix those little metal angles in exactly those points where the roof sheets are currently already fixed, which is important. That's otherwise of this system. How are they fixed? No, the question was how will they look? They basically, what we are going to do is we are removing the bark, and then that curved side is the one that faces up, and they are installed in two layers. The first layer is slightly spaced out, and then there's a second layer with a member on top. So it's essentially a staggered look. And how are we treating them? How are we treating the makoko? No, no, we are not treating it at all. This is essentially a, you know, the property or the whole quality about wood is that there's not really a big problem with wood getting wet. Wood is quite good at getting wet. What is not good if it can't dry. Now, if you install it in a way that there's air all around, especially in the case where it is exposed to the sun like a roof is, it will not actually rot that fast. But it should also be said that the client knows that this is of course a natural material that we're using in a roof, and it is not going to be there for 50 years. The argument was that it is not the actual essential waterproofing layer of the roof. It is an additional layer. So even if it fails here and there, it will not actually affect the performance of the building. And the second advantage of this technology is that you do not need to have any specific special skill to replace makoko here and there, because everybody knows how to do that and you can buy that stuff in the next village. So it is a very cheap, simple material that can be replaced if need be by the school's facilities manager or by a local carpenter without much complication. I think we are going to move into the multi-purpose space and from there towards the toilets.
So there's a question here. Children tend to explore at certain ages. How will the wall finish, lime and earth plaster survive tough knocks and or pokes?
I'm just going to wait till all members have joined us here. Edson, we have a question. Answer it. I think it's a great question. It is essentially lime earth plaster suitable for this application with children. Children tend to be quite rough and they play and they explore and they climb and they do things. The short answer is that we are really positively surprised how strong our samples are so far that we have managed to achieve in terms of their hardness and durability. Number one, and Edson can probably say more about that. And number two, and that is really an important aspect, we always need to think about what is the process of repairing damages and of improving, of maintaining a building. There is nothing easier to maintain than earth plaster. What is very complicated is to fix cement plaster that has broken out and that then needs to be painted over, and by the time you paint it over, you actually need to paint the whole wall and you need to go and buy 20 liters of Plascon paint. We don't need all of that. We can actually repair locally in certain areas with material from the site. That is one of the big strengths that I see in earth plaster. I think Edson can say a bit more about the stability or the durability.
I must say that if we get it correct, especially the final layer, which is the layer, the lime plaster, it's a rock if you get it properly. If you actually install it properly and cure it properly, it gives you a perfect rock. Of course, if you don't do it properly, then it will powder away, in my view. But comparable in strength, you can get as strong as a plaster as you would get from cement. So we're also not using any sharp corners. What you see here is just all the corners. Wherever we have actual corners, we will curve them in a quite smooth radius, which will further help. We are standing here, by the way, multi-purpose. We have created that in between the pairs of classrooms. There will be some built-in stone benches on the sides. And the idea really is to, in the absence of some kind of assembly hall or a small dining hall, which the school will not have in phase one, this is a small covered external space that can be used for flexible learning, for hanging out during break time, for playing, but maybe also for a bit of teaching. We shall see how the school will use these spaces. Great. I think now comes the toilet. It's a bit weird to end at the toilet. So there are maybe two interesting aspects to talk about when it comes to the toilets. One is that all these toilets are connected to a biodigester. And two is that we actually designed these buildings as almost as a mock-up building. So in other words, we decided that we wanted to use every single technology that we're using in the school already in the toilets, and we learn while we're doing it, and then we roll it out in the actual building. So these tiny little buildings have earthbag walls, they have stone walls, and they have wattle and daub walls, which is a technology that we want to use in some of the partition walls in the admin section. So we basically chose to squeeze that all into one little building. So obviously the major rectangle that you see there, which is now started to being plastered, that is an earthbag wall. It has the vertical poles in it, a bit similar to what we have seen in the mezzanine structure. Then we have, as a privacy screen, we have a rubble stone wall. So the wall that you see here is entirely made out of stone, obviously though with conventional cement-based mortar. It has lime. Okay, and lime. And what we are trying to do here is we basically use this building to learn what is our preferred way for this project of dealing with the stone. And we developed this idea of using the big block slates in the corners, and then transitioning into the wall, we are joining normal thin slates. And we quite like that look, that sort of strong look it gives to the corners, and really showing that this is actually a stone wall and not just a clad wall that has a problem in the corners where the two slates don't know what to do. And then we have, as a toilet partition wall, we have the wattle and daub, which is, in my view, still the technology that we should all use most. And we should all learn from it, and we should all reinvent it in a proper way, because it is immensely cheap, immensely lightweight, immensely fast and stable. It has so many, which is primarily the moisture that enters the primary timber structure from the bottom, that once we have resolved this, I really feel this is something that could be adopted in a bigger scale. So that is one of the reasons why we used it here in a very small scale, because we wanted to start learning
how it is done. What's our lesson learned on the wattle and dough bowl?
We're keeping it stable, especially the frame, because it really relies on the framework, and the earth is more like a field or a partition, if you must. So the frame has to be stable, which we have failed here. I think the first framework was removed and redone. And of course, when you want to keep these things off the floor, then you need some steel brackets and some nasty connections, and which actually kind of makes the whole thing not very stable, as opposed to what a villager would do just by ramming this thing into the ground. But of course, then it will rot. The termites will enter through its pore and all. Yeah. So this is actually built off a concrete floor, and off all stone foundation and stuff. Yeah.
One of the reasons why we struggled with the stability is that we are trying to the biogas system has a, we are dealing with it, but we will get there. To the bio toilets, you can see that these toilets are aligned, and then there's a further toilet block up at the top of the site where the teacher's accommodation is. So all these 3 blocks are connected by an underground pipe, and then you have these hand washing sinks that are also made out of stone, and the hand washing is actually only in the 2 left compartments, and the one on the right is the flushing tank. What we are doing here is that all the gray water from hand washing is collected in this holding tank, and then there's a certain flushing mechanism that can be pulled twice or thrice a day actually, and that will push the water through the main collection pipe and flush the waste down the hills. So these are essentially, in the way they feel, these toilets is very much like dry toilets, like latrines. But the difference is that they are actually being flushed thrice a day, and that the matter is being moved down the hill into the digester, which is, I think, about 150 meters further down the hill.
Speaking of water collection, there's a question here by Norman, who said that the roof has, the buildings have a large roof surface area. So how are you collecting and utilizing the water?
We are collecting and utilizing it. So what we will install is steel gutters, galvanized steel gutters. You may have noticed that this roof edge is actually not horizontal, not straight. It is zigzag, which will give us a natural fall towards one point. Every second, every zig, if you want, we will have a spout. That spout will have some chains hanging down, and then we are making some very beautiful earthen concrete receptors that resemble a little bit the traditional village rainwater collection tank. And through that, we are going to collect water. We will have a pipe running along each side of the building, and then we're actually running a collection pipe all the way down to the site to a centralized rainwater collection tank. That's the design in short. So yes, we are using it. We are then pumping it using solar power. We're pumping it up to the site where we are building a gravity tank.
I'm just curious, how are you achieving this small joint between the slats? Are they being cut?
If Costa was here, Costa. I think first and foremost, we are achieving it because we have a very patient man called Costa on site. This is Costa. He's asking, are you cutting all these edges?
Not all.
Not all.
Yeah, not cutting all. Yeah, just the shallow.
So essentially what we are trying to achieve is joints that are as small as possible. And in essence, what that requires is a lot of patience, because you need to find the right stone. You cannot just go and use whatever you find. You really need to find the right stone. I think this is a good example of a wall there, where you actually see, I hardly see any cut. I see one cut side there, but there's really very few cut shapes. And I feel that, yeah, we are very keen on that. We don't like these very wide joints that are smeared with mortar that you see, and very often even painted and sort of making a statement out of it. I actually feel we should show the skills that are there, or we should develop the skills that are there and really do some crafted walls.
When you mentioned the wall being lightweight, what did you mean by that?
So wattle and daub walls are essentially they are not lightweight at the end, but they are basically made of a very lightweight framework, a primary framework. So you've got vertical gum poles normally very often. Then very often you have a bamboo grid that you put across. That weighs nothing, that material. And you put that very quickly up. And then you slam against it an earth mix. Now, that earth mix comes from site. So it's not lightweight then, but it is from site, and therefore it doesn't involve you transporting, tons of materials across the country. So in that sense, I find it is a very, very interesting technology for us, because we end up not with having walls that are 0.5 meter wide like earthbag. We're having walls that are normal, 100 mil, 150. You saw how these walls are actually already a bit thicker than we thought because of this bent pipe, but actually I think they could be 150. And you can, as long as you manage to sort out this moisture issue, if you get this stuff off the ground, then I think this is a very, very good technology for Uganda. It has all the thermal benefits that earth construction has, but it doesn't have all the complication that other earth construction technologies have. I hear one more question, because we are coming to the end of our session. Is there any more question? Or yeah, here.
With the, I'm sorry to take you back to the way the stone has been done, but with this little space here, how do you deal with it over time in case maybe some insects or algae begins to grow in those joints?
Well, as I mentioned before, we are not actually leaving them completely open. We are going to put in an earth mortar basically for visual reasons. And that earth mortar is going to be slightly recessed in, and it will combine it with the earth plaster from above. That's the whole idea, so that we really tie them together on an architectural level. And that means there are no big cavities or anything like it. A bit of algae, and it depends on the way. For instance, this side will probably be exposed a bit to the rain, so a little bit of weathering of stonework is perfectly acceptable and perfectly okay. That's the whole beauty of stone. It can deal with it, so we are not afraid of that. It can also be cleaned off any time if people want to. Sarah.
Fantastic. So I think that concludes our event today. Thank you to everyone who's here physically, those of you who are on Zoom and Facebook. Like I mentioned earlier, we have been recording this, so we will be sharing a link with you so you can rewatch in case you missed any parts of it. Yeah, thank you. And then we'll have another session in September. So that's the 3rd Wednesday of the 3rd week of September. So if you're part of our newsletter, we'll get that information straight to you. And if you'd like to be part of our newsletter, feel free to email us at sarah@localworks.ug, or you can reach out to us through any of our social media. That's at Localworks UG on Facebook and Instagram. Thank you.